So let me give a quick introduction to Dusk for you to understand the context. So Dusk is an open source blockchain infrastructure that is built so that businesses can use it to tokenize financial instruments and automate costly processes. So essentially, Dusk is technology built for securities. And the issues that we have at Dusk, I think they are not shared in most cryptocurrencies because since they are intended to be used for regulated markets and businesses, they need to, on the one side, comply with the current regulations and laws, and on the other side, privacy is really important. So it's not just an option, but businesses and like the financial markets, they do need the privacy. So in this context, today I would like to talk about which is the transaction model that is used in Dusk. Sorry, I will remove my face mask. I forgot. So before I explain the model, I would just like to make the difference between the two main models that we have when we build the blockchain. On the one hand, we have the account-based model, which would be, for instance, Ethereum. And this is very similar to the way we think of the money that we have in the bank. So if you think, how much money do you have? You probably go to your account, you see how much money you have, and you have a balance, and that's the absolute value. And then that balance may change depending on the transactions that you get or that you send. So it's essentially a number that rises or decreases depending on, that changes over time, right? So this is the idea in Ethereum. We essentially have a set of people. They have their own accounts with their own balances. So every time there's a transaction between people in the network, the balances get updated. So in a state K, we had these previous balances. After these transactions, the balances get updated, and this is the newest state of the blockchain. Okay. So during the presentation, I'll try to be precise, but I may omit many details. So if you want to know further things, you can ask me later. So the way this is stored is using Merkle trees. So we would have each of the balances that will correspond to each of the leaves of this tree. And then all the nodes of the tree are calculated doing the hash of their siblings. Okay, so for example, in the previous example, if these people from the network, they make these transactions, we need to update the balances, which will mean that all the leaves of this Merkle tree will have to be updated. And every time we update the leaf, then the corresponding parent will also be updated. And at the end, the root will change. So in the next state of the blockchain, we will have a different root. So we identified the state of the blockchain with a root in the Merkle tree. This is one way of thinking about money. We just have balances. We increase the values or decrease depending on the money that is being transferred between people of the network. And another way of thinking about money is more like when you think of the money that you have in your wallet. Rather than a total amount, you would think of money as a collection of coins and notes that you can spend. And then if you go to a shop, depending on how much what you're buying costs, then you may take a number of codes or a number of nodes or a number of coins depending on what you want to spend, right? So this is more similar to the other approach, which is the unspent transaction output model. For example, this is the one that Bitcoin uses. So in this case, we would have the blockchain, and at state K, we have, for instance, 3 different unspent transaction outputs. Each of them have a corresponding value. The status, the U, means that it's unspent, so no one has spent these outputs yet. And who are the receivers of each unspent transaction. So, for instance, imagine that now Alice, who's holding an unspent transaction number 1 of 120, she's allowed to spend it because it's unspent. And now when she sends a transaction to someone else, imagine that she sends it to Bob, what she will do is make a transaction saying, okay, I'm going to spend this unspent transaction output, which is worth 120. I am the owner of that unspent transaction. And my output of this transaction is going to be 80 for Bob and 40 for herself, because she wants to keep the change, okay? So in this case, once this transaction is done, the blockchain would be updated to the newest state, and the blockchain will identify that the unspent transaction output number 1 was already spent, and instead it will add 2 different unspent transaction outputs, one corresponding to Bob and another one to Alice. Okay, so that's the idea. And essentially you can think of this as a set of, from now on, like when I explain Dusk, instead of calling them unspent transaction outputs, I will call them nodes. This is why I'm saying all the time nodes, because to me, this is like you have a collection of nodes, one worth 10, one worth 120, 55, and so on, and you decide which is the one you want to spend. And once you spend it, you can either decide to spend all you have sending it to someone or sending a part and then you keeping the change. So when we have these kind of transactions where everything is transparent, a transaction is pretty easy. So you say, okay, imagine we are Alice and we say, okay, I want to spend this unspent transaction output. I want to send it to Bob. So I will create a new unspent transaction so that he can spend it. So the network can easily check the following things. First, that this unspent transaction does exist, that it has not been spent yet, that she was indeed the receiver of that transaction, that the new output is valid, so the new unspent transaction output is really sent to Bob, and also that the money sent is the money spent, so that Alice is not sending more than what she has. So all these checks are pretty easy because you have all the information, it's transparent, so not much to say. The network can check that everything works as it should. Before I continue, this is the only thing I will say about math. So most of you are probably familiar with this, but just in case. So for sending money to people, we always use public, secret key, and well, like we have like all these basic primitives that we are very used to use, but maybe some of you don't really know how it works inside. So let me take the opportunity to mention how this works, more or less. I'll try to be precise. So an elliptic curve is essentially an equation. It's a set of solutions to an equation that usually looks like this. So apart from all these solutions, we also have a special point, which is called a point at infinity. And the important thing is that once we have the solutions to this equation, we should be able to make operations with these points. So let me explain how we add points by using an example. So let me start by that point there. I will call it G. If I want to add that point to itself, what I will do is that I will draw the tangent line. I will see where it intersects with the curve. And then I will do the reflection, and the resulting point is going to be 2G. So it's G added to itself. So we started at G in the orange point, and then we ended up in the blue point, which is 2G. So if now I want to compute 3G, what I could do is add G to 2G, right? So I would get 3Gs. So now instead of the tangent, we draw the line that goes through the 2 points, and we see where it intersects. Again, we do the reflection, and the resulting point is going to be 3G. So we started at the orange point, then we went below, then we went up, and that was 3G. So if we do the same multiple times, so we keep adding G to itself many times, at some point, we will end up somewhere in the curve. And what is key here is that if we know where we started, so if we start at the orange point and we end up in the latest point, so in this case, the blue point there, this means that we looped around the curve a certain number of times. I'll call it K. And what we assume is that if we know the starting point and we know where we end up, we don't know how many times we went through the curve. And that's the discrete logarithm assumption. So if I know P and I know G that satisfy a formula like this, it's very difficult to retrieve K from here. So we usually use K as a secret key and P as a public key. This is the case in the Bitcoin network. So we take a private key, which is a number, then we multiply it by a point, which is called G, and then we get a resulting point. So you can think of it as the blue point in the curve. And then from there, we derive what is called the Bitcoin address, where we essentially hash our public key. So if you think of this sequence from the Bitcoin address, no one can know what was the public key that was originally used to derive the Bitcoin address, because it's a hash. So it's very difficult to get the pre-image of a hash. So although we can see addresses, we don't really know the public keys. But there is a trick here, and is that every time that we send transactions in the Bitcoin network, in order to transfer funds from our addresses to another address, we need to show that we are the owners of that address. So somehow we need to show that we are the ones who know the private key that was used to calculate the Bitcoin address. And the way we do that is by using signatures. So if we make a transaction sending funds from an address to another one, we should sign the transaction with the keys that were used to calculate the address we are transferring the funds from. So what this means is that every time that the transaction is included in the network and is validated, the public key becomes publicly known. And, well, if you want the network to be anonymous, people claim, well, you can have as many different Bitcoin addresses as you want. The only thing you have to do is to keep your public key completely independent from your identity. But there are several problems with that, and we know that there's been a lot of studies saying that it's not that difficult to trace most of the accounts in the Bitcoin network, for instance. And to me, what I see it's really a problem is not that once you know the address, you will get the transactions, you will track that person, is that you have the whole historic of what happened. So once I know a public key, I can look at the whole blockchain and see how much money everyone in the network gained or shared or transferred and everything that happened. So at Dusk, we decided to follow the Zcash approach, which is essentially they base their protocol on Bitcoin. The only thing is that they make payments anonymous by default, and that's the same approach at Dusk. So in a similar way, instead of keeping the balances of the accounts, we keep the unspent transactions outputs, which I will call from now on nodes. Okay, so in each of the nodes of the Merkle tree, we will have the hash of the different nodes. And we use this tree to keep track of which are the nodes that were created. So only the nodes that are stored in the tree are the ones that can be spent. When I say that I send money to someone, what I mean is that I'm creating a new node that will be added to the Merkle tree. And when I okay, I have the same definition here, sorry. So when I spend a node, I mean that I'm spending a node that is in this Merkle tree, and when I'm sending money to someone, I am creating a new one that will be added to the tree. So how do we do this? Well, a user will have to show that the node is in the tree and that he is allowed to spend the node. And the key here is that we don't want the user to reveal which specific nodes is spending. So what this means is that the network will keep track of all the nodes that were ever created. The network knows that some of them are already spent, but they don't know which ones. And we have to make sure that everything is done within the rules of transacting. So this means that we should be able to check that, okay, the value being transferred is okay, I'm sending a node that is really in the tree, I am the owner of the node, I'm not doing double spending, so that all the rules follow, okay? And the way we do this, as most of you know, is that we use zero-knowledge proofs. So just a quick introduction and very informal to zero-knowledge proofs. So a proof essentially allows a prover to convince a verifier, so it allows one party to show to another that the statement is true without revealing anything else beyond the veracity of the statement. So this is the general definition. And the way we put these proofs into practice is that we model our statements using arithmetic circuits. And this is what I'm actually going to present today. So just to give the intuition, we can think of an arithmetic circuit in a very simple example. We have a private input. In this circuit, we make with operations, additions, and multiplications a hash function, and then we get an output. So here, we can use this circuit to show that we know an x, which was the input, satisfying this circuit that had an output h. So we can use this circuit to show that we know the preimage of a hash function, for example. Okay, so when I say private, it means that is information that we don't reveal, and when I say public, it means it's information that the verifier knows. Okay. So the goal today is to design a circuit that will allow us to show that a transaction has been performed correctly, so following the rules, but without revealing the payment details. And by payment details, I mean which of the nodes is being spent, who is spending, and who is it sending it to, and what was the value of being transferred, okay? So as I explained before, so if we want Alice to spend a node and create a new one for Bob, she will have to prove several things. Instead of having the network verify all the checks, because all the details of the transaction will be secret, it will not be the network who will do the checks, but it will be Alice. So Alice will create the proof ensuring that all these checks are okay. Okay, so on the first hand, she needs to show that the node she was willing to spend is in the Merkle tree. She has to show that she is allowed to spend the node. She has to make sure that this node will no longer be spent again. And she has to create a new node for the receiver, Bob in this case, and also that the money sent is the money being spent. So let's try to see how we prove that the node is in the tree. This one is not very complicated. So for example, in this case, imagine that Alice is the owner of node number 2 and she wants to spend this one. Typically, an inclusion proof will be the nodes that are in red, so she will have to provide these other nodes. And then the network, using this inclusion proof, they can recalculate the root. So if the calculation matches the root that is in the tree, it means that the proof is correct and the node number 2 is in the tree. So if we build this as a circuit, so she will have to provide all the proof. So all the inputs of the proof will be private. We essentially keep hashing all the inputs until we get, so, well, that arrow at the very end is the recalculation of the root, and we need to check if that matches the root of the tree. So we need the root to be public in order to check if that node is really in the tree we are looking at, okay? So the output you can see that is public, so we know if the input sent by Alice really matches the circuit or not. So let me say that if we do this, we don't know anything about the elements that we send in the proof. So we don't know which of the nodes is it that we are sending. Okay, so we just know that it's in the tree, but we don't know which one because we don't know any details of the path of the tree. So the other thing she has to show is that she is the one allowed to spend the node. So in order for me to explain what does it mean to own a node, we should know what a node is in the first place. So a node consists of 3 elements mainly. One is the commitment of a value. So how much is that node worth? There is an element called R, which is a point in the curve. And then what we call the node public key, which is a public key that is associated to the node. And this is the important part. So the node's public key will be a public key that is associated to the node, and only the person capable of calculating the secret key associated to it will be able to spend the node. So every user of Dusk has the following keys. You can see the secret and public key are pretty standard. The only thing is that we have them twice. So we have 2 secret keys and 2 public keys. So a double of 2 each of them. And the view key is a combination of one part of the secret key and one part of the public key. Okay. So how does Bob identify that Alice is sending money to him? Because he doesn't see his address in the transaction. So how can he know that he is getting money? What Alice would do is that she would choose a scalar at random. She will compute a new point, and then the node public key will be computed the following way. So she will hash his secret R together with Bob's first part of the public key A, multiplied by the generator, so that the result of this operation will be a point. And then she will also add the second part of Bob's public key. So NPK is actually a point in the curve. So what Bob would do is that every time he sees that there is a node on the network, he will check if using his secret key A, note that small a times big R should correspond to small r big A. So this is just Diffie-Hellman. Added to his second part of the public key, he needs to check if that operation corresponds to the NPK that is part of the node. If that is the case, he knows that he is getting the node. And this is important because you can see that Bob does not use either the whole public key nor either the whole secret key. He uses what I call the view key. So it's just the first part of the secret key and the second part of the public key. So once he has this, he can compute what's the node secret key by just removing the G there, and instead of having B large, he can take the second part of the secret key, okay? So you can see that if you multiply NSK by EG, you will actually get the node's public key. And the important thing is that for him to see that some money has been sent to him, he only needs the view key, but in order to get the node secret key, he needs his whole secret key. And that's interesting because what he can do is that he can actually share his view key with, yes? Ah, okay. I'll be quick. So he can share his view key with a separate entity so that they would scan the transaction for him, the transactions, and tell him which nodes he is getting. But even if he shares the view key, he should share the whole private key in order for that entity to spend the nodes. So by doing this trick, we allow to delegate the scanning of the network, that job, to a separate entity while still making sure that no one else can spend the money that he is receiving. So for ownership, this would be the secret. So essentially, he has to show that he knows the secret key associated to a public key. And for that, he needs to take his whole secret key, put it inside the circuit, do these operations. So NSK will be computed inside the circuit. And the circuit checks if that secret key does really correspond to the node's public key. And if that is the case, we will get a true at the end. So here I'm just adding it to the previous circuit. So here we are making sure that the node's public key is the one that is actually used to check that it belongs to the tree, so that we are not making any tricks here. And what I wanted to say is that here we are making Bob, so he needs to insert his secret keys inside the circuit, which is not something that we would like to do. So instead of doing that, we will make a trick which will consist of making him sign a message with the node secret key in order to show that he's allowed to sign a message with the secret key, but without putting it inside the circuit. And for that, we make a very silly trick, which is the double Schnorr signature, which is a trivial extension of the Schnorr signature. It's the same Schnorr signature. The only thing is that we have two parameters. One by G, so we make all the construction of the signature with a generator G, and another one with a generator G prime. So it is essentially the same, but from the same secret key, we derive two different formulas, one with G and another one with G prime. And the message that we will use will be the hash of the transaction. So now the circuit becomes a little bit easier. So instead of ensuring that Bob is the owner of the node secret key, the circuit will verify that he is able to sign a signature using that key. Okay, and you would ask, why do we need the double Schnorr and not Schnorr is enough? I mean, we already have NPK, so why do we need this NPK prime? And the reason for this is that we use NP prime to derive a nullifier. So let me just remove this, but essentially a nullifier is just a serial number that will prevent the users from spending the same node more than once. So this is what he will do. From the node's public key prime, which is a unique deterministic value, we will hash it and we will get the nullifier. And the key here is that from the nullifier, no one can retrieve which was the node that was being spent, not even the person who sent it to that person in the first place. Finally, when doing a transaction, you're spending money and sending it to someone, so you also need to make sure that what you are sending is right. So we compute the commitment of the new node that is going to be sent inside the circuit. Finally, we need to ensure that the values being spent and sent correspond. So we just subtract, we see if it's 0, and if that's the case, we will get it true. And the last check that is already solved in the circuit I show you is that we want to make sure that no one is going to change the transaction, but since we are the details of the transactions, but since we are signing the hash of the transaction, we know that no one will be able to change the transaction because otherwise the hash will change. So the hash of the the double Schnorr signature that I showed you also serves for this purpose because it ensures that the hash of the transaction is already bound to what is being sent. And I'm almost done. So it is the final circuit, and I just wanted to say that the first part goes for minting, so what's the money that you are creating for the person you're transferring to, that you make sure that you are not spending more than you have, that you are the owner of the node, that that the node is in the tree, that you are the owner of the node, you ensure that the transaction will not be changed by the miners or anyone afterwards, and finally you get the serial number that will prevent you from spending the node more than once. These are the properties of the system. Well, it's mostly what I said, so I'll just skip it. And if you want to know more about how Dusk works, or I just presented how it works with the transactions, and there are multiple features, so if any of you is interested, you can take a look at this. And I think I made it. Any questions?